Recording. And great. So it's my pleasure to welcome Markus Pilman here. He's an alumni of the systems group. He did his PhD with Donald Kosman on distributed key value stores. And today he's going to be telling us about FoundationDB, where he's working on that from Snowflake. It's an open source project, and delighted to have you here, Markus. So thank you.
Thank you, and thanks for the introduction. So yeah, welcome, and thanks for having me. I'm sorry, my cat is just getting on my desk now all the time. So yeah, I'm working for Snowflake, which I started doing right after my PhD. So I've been there for 5 years now. For those of you who don't know Snowflake, like I promise, this is my only marketing slide. Afterwards, it gets technical, but basically Snowflake, like the core product that we are offering, is a data warehouse in the cloud. And these are kind of like the founding principles that we wanted to have, right? So it's a complete SQL database. Data warehousing means we are optimizing for analytical workloads, which means that we are not optimizing for many low latency queries and point insert, but instead for very large queries that scan a lot of data. Like that's kind of like the most intuitive way you can distinct these two from each other. And it has no infrastructure admin costs for our customers. It's fully managed. There are like no knobs, no indices or things like that, or partitioning, vacuuming, all of these things fall away. So you can just like go ahead, like register at Snowflake and start running your queries, and all of them should be fast without you doing anything special. So that's kind of the sales pitch. What is FoundationDB? This slide here is a bit of a mouthful, but don't worry, I will explain these like most of these concepts later. But basically, it's an open source project. It used to be closed source, and FoundationDB used to be its own company that then got acquired by Apple, and Apple made it an open source product. It's a distributed key value store optimized for LTP workloads. And it has a very simple schema. So we are basically just mapping byte arrays to byte arrays, right? That's all it is. So think of like if you're in the C++ world, it would be an ordered map of string to string. We support range queries. So this is why it has to be ordered. And we support strict serializability. So serializable here means that the outcome of like 2 concurrent transactions is equal to some serial execution of 2. And strict means that transactions are strictly ordered. What this means is if you have 2 machines and one machine commits a transaction and afterwards another machine starts a transaction, it will see these writes. And FoundationDB achieves that through a mix of optimistic concurrency control and multi-version concurrency control. And I will explain later what that means and how FDB does that. It's probably its main feature, and the main reason Snowflake uses it is that it's incredibly robust. The main limitation is that transactions can only run for at most 5 seconds. So if you use this as an internal product, that's actually a great feature. If you want to sell this to customers, then it's probably a hard sell. But like typically, if you have an OLTP transaction that takes longer than 5 seconds, I would tell our customers, which are like internal Snowflake folks, that they are doing something wrong and they should rethink their workloads. Okay, so this is how like the Snowflake architecture roughly looks like. So we are storing our data on blob storage, so S3 on Amazon, for example. And this data is stored in like files of relatively large files of like 16 megabytes each. And if you think of like a table in Snowflake, then each row within a table is stored in one file. So we don't do like a columnar store. However, within a file, the data is organized in a columnar way. So this is very similar to what we otherwise would call the PAX layout. And this allows us to do a bunch of like interesting optimizations. Then the next layer is the virtual warehouses, which are basically just compute clusters. And if you are a Snowflake customer, this is basically what you're paying for, right? And you can have as many of those as you want, and you can size them. You can have larger or smaller ones. And these are actually executing the queries. And then above that, we have the layer that we call global services. And this one contains stuff like a load balancer, the SQL compiler with the optimizer, the transaction manager, a security layer, and the metadata layer. And the metadata layer is what runs FoundationDB. And so the interesting things here is like, if you look top down, right, your query comes into the top, it goes to the SQL compiler, which creates a query plan, and then it gets pushed to your virtual warehouse, which executes the query. And so the interesting thing here is we have a separation of storage and compute, which means that on the same data, you can have as many of these compute clusters as you want to. So if you want to scale up, you can just create more of those, and then you can run more queries in parallel than if you only have like one. So it's very elastic, and you also can shut all of them down, and then you don't pay anymore. You only pay for data, for storage, and storage is very cheap. And then we have a separate metadata layer from this storage and compute. And above the metadata layer, everything is just stateless services. So which makes a lot of things very easy. So the SQL compiler doesn't have any state in it, like on disk somewhere. So if we lose a machine, we can just restore it somewhere else. And so FoundationDB is, as I said, is here the metadata layer. And just to give you an idea of how much usage it gets, we sometimes joke that FoundationDB is the largest database you've never heard of. At Snowflake, we have around 50 clusters in productions and hundreds of clusters in like QA and test deployments, etc. Our largest cluster runs on around 360 CPUs, roughly 200 disks. It stores around 10 terabytes of data, and then that's triple replicated, right? And it executes around 200,000 transactions a second. That is not very impressive, right? Like for the like size of the cluster, like if you look at the workloads, that doesn't look like a whole lot, which is mostly due to us being paranoid. But like I like, if you have questions afterwards, I can go a bit into more detail why it is that way. But there are other large FoundationDB users. The largest one is Apple iCloud. And the way Apple uses it is like basically all iCloud data is stored in FoundationDB clusters. And they create what they call logical databases. And they have one of those for each user and application pair. So they have billions of those, right? Because Apple has many, many customers. And so as you can imagine, Apple runs even more FDB clustered instances than we do. I cannot give you exact numbers because that's sensitive. Then there's also like VMware uses this for the product called Tanzu now, formerly Wavefront. IBM does a bunch of stuff with FoundationDB, eBay, Epic Games, and there are a few other ones that are using it. But the two largest ones are Apple and Snowflake, and these are also the two largest engineering teams around the product. Okay, so how did this work at Snowflake, right? So Snowflake got founded in 2012, and initially, we used MySQL as a metadata store, and that didn't work well for various reasons. And so in 2014, FoundationDB acquired its first few customers, and one of them was Snowflake. And so we migrated our MySQL storage to FoundationDB. In 2015, Snowflake became generally available. In 2016, well, that was the year I joined, like we had more customers. FoundationDB already was bought up by Apple. We didn't have engineering support anymore, so we started to build an engineering team around FoundationDB, of which I was the first employee in that team. And then in 2018, Apple open sourced FoundationDB, and we integrated all of our changes back into open source and migrated our clusters to the open source version of FoundationDB. So why did we choose FoundationDB? Like it's very simple and flexible, and simple here is a good thing, right? And we have transaction support. We have reasonable performance, and it doesn't need a whole lot of tuning. Like you can just run a cluster and you get something that is reasonable. It's probably not the fastest thing in the world, but it's fast enough for what we are using it for. It can do things like automatic data rebalancing and repartitioning, so it keeps our data safe. And as I said before, this 5-second transaction limitation is a blessing in disguise. Because if you have a lot of long-running transactions in an OLTP system, eventually you will run into troubles. And FoundationDB just doesn't allow those. And so we don't have to, like in hindsight, figure out why the database is like struggling with long-running transactions, etc. Okay, so what I said metadata in Snowflake a lot. So what does that mean? And so the way, and there's a SIGMOD paper about that if you're interested in like more details, but very high level, the way it works is Snowflake does copy and write for data. So we have this data that is stored on in S3, and when the customer writes a query to modify some data, we take these data files and rewrite them into new files. And S3 doesn't give us like transaction support. So if you have to rewrite many of those files, you cannot do this atomically. And so this is where FoundationDB comes in. FoundationDB basically stores pointer to these files. Like that's a very bird's eye perspective. It's a bit more complex than that. But high level, that's kind of the idea. You store pointers to those files, you rewrite the files, and then when you want to commit your transactions, you can do that in like one FoundationDB transaction, and therefore you can drive the transaction semantic through another transactional system. There's also we also store encryption keys in FoundationDB. So that should tell you that it's like very sensitive, that we cannot lose FoundationDB. It means that if we lose data in FoundationDB, we won't lose customer data, but we won't be able to read customer data anymore, which is kind of equivalent, right? So yeah, I won't go into details here. Like the whole security concept is something that is a bit out of my competence. But again, there's a great description of it in the paper. So this was basically about Snowflake and how we use it. And now I want to go purely and talk about FoundationDB, which this talk should be about, right? So as I said before, like this is kind of a mouthful, but FoundationDB provides strict serializability through optimistic concurrency and multi-version concurrency. And I want to quickly explain what that means. So optimistic concurrency control, like from a very high level, what that means is that you can run a transaction optimistically. You never stop your transaction until the very end. And at the end of the transaction, you decide whether you can commit or not. And if you can't, then you return back to the application and tell it that it has to retry. And this is usually great if you have a workload with very few, which produces very few conflicts. It's usually not so great if you have something that is very conflict heavy, because you can run into starving issues. But the way this is roughly implemented is, if you look at all your committed transactions and you write them into some kind of log, right? Then when you start your transaction, you will have some start time, and you will know the most recent transaction at that time when you started. And then you're running the transaction. While you're running it, some other transactions are committing, and all these transactions that are committing at the time, I'll call here the conflict zone, right? So everything here could conflict with our currently running transaction. And then when we attempt to commit, we attempt to add it to the tail of our log. And now we have to verify that there's no conflicts between like the start time and the end time. And the way FoundationDB does this is it looks at all writes that happened in between, and it checks whether we did read anything that was written in between. So we are checking purely for read-write conflicts. And if you want to get serializability, you have to check for read-write conflicts. You cannot just check for write-write conflicts. And we actually are versioning these. So each of these boxes would get a version assigned. And we have one process in the cluster that acts as a clock to assign those. Multi-version concurrency control is a bit easier to understand. Basically, what we are doing here is we version the whole database. And then on each commit, we create a new version. And at the start of the transaction, we assign this version, like doing this strictly. So if you go back, if you look at the start time, like finding this start time and actually getting the very last entry in the transaction log, this is actually what gives you strict serializability as opposed to just serializability. And so we assign this version to the transaction. And then whenever we read something, we read at that version, which also means that if we never attempt to write anything, we can always commit because we don't really get any conflicts in that sense, right? And so it would be kind of a snapshot read. The way this is implemented in FoundationDB is, I said we have only 5 seconds a transaction can at most run 5 seconds, which means we don't actually have to version the database forever. And so in the storage layer, we shard our data across many of these storage nodes, so we can have hundreds of them. And each of them has an on-disk B tree, which is on version. Currently, this is SQLite, the B tree of SQLite. We don't run through the SQL engine, obviously. And so whenever we have to read from there, we cannot do this in a version break. And then on top of that, we have an in-memory tree. This is implemented as a tweak, which is a very interesting data structure. If you haven't heard of it, there's a Wikipedia article that explains it pretty well. But it's like a special tree which can do versioning. And so this one will keep the last 5 seconds of updates in memory. And so when we read something, we first read in memory, and then we read on the B tree, and then we merge the 2 results together for range queries. If it's a point tree, we should first check whether it's in the in-memory tree, and if it's not, then we go to the disk. And if something gets, like if a transaction comes in that is older than 5 seconds, we can detect that and we just send back an error, and then the transaction will abort. Okay, so now I want to quickly walk through the lifetime of an FTP transaction, like how this works from a bird's eye perspective. And I will leave out quite a few details here, mostly because otherwise this talk will easily take like 4 hours. Just like the recovery algorithm, if something fails in here, is, as you can imagine, pretty complex. But so we start with an application that runs on some client, and our client is a fat client, so it itself includes quite a lot of logic in order to drive a transaction. And so the first thing it does is it asks a special FTP service, which we call the proxy for transaction version. So for read version is what we call it. So it sends a start transaction request to this proxy. And this proxy will send back the most recent version of the database. And this is one detail that I leave out how we do this, because this is actually pretty complex and also pretty expensive. And then we just remember this locally in the memory of the application. And so now if we want to read something, right, we have a bunch of storages, and we don't really know which storage has the data that we are interested in. And so we will ask again the proxy, hey, I want to read key foo, where can I find this key? And then this one would say something like, oh, all the keys between A and G are in shard 2. And so this is obviously, we have the choice here of 3 storages if we triple replicate, but now we know where to ask for. And we will cache this. So after a while, when this cache is warm, we will know about all the shards, and we can just go directly to the storages. So we don't have to do this every time. Obviously, if data moves, then we might go to the wrong one, and then we have to invalidate the cache. And so now we go to one of these 3 storages. We don't have to do a quorum read. We will just take one of them. And the client does quite a complex load balancing here by having like a latency model in memory. And note that we only read from one. So if we have a warm cache, then reading a single key from FDB means you need exactly 1 network hop, which is pretty optimal. So for read heavy workloads, FDB is actually doing really, really well compared to a lot of other systems. And so we will tell this storage server, we want to read foo at version 200. And so the storage server will then reply with the value. And again, we will cache this locally in the application. So if we read foo again, we can just return it without talking to it, because we know that during a transaction, this value cannot change. And now if we want to do a write, we don't do anything. We just remember that we want to write this. So we write like this change into the memory of the client. And so, but eventually we obviously want to write this back. And so we need to run a commit. And so now here comes the most interesting part, which is the commit protocol. And so we send the read set, so all the keys that we read, and the write set, so everything that we have written to, plus all the mutations that we know about to the proxy, and tell it, hey, we want to commit this, we want to write this back. So now the proxy needs to create the new version for this commit. And for this, it goes to a special role called the sequencer, which is basically just a process, a single threaded process that runs a clock. So it will just increment versions. It takes time into account, so it will increment versions by 1 million per second. And because it runs in a single process, it will be serialized, right? And so this thing will like reply with some version to the proxy. Keep in mind here that clients never communicate to the sequencer directly. And the reason for that is because that would overwhelm them very quickly if you have too many machines talking to them. We also don't want to do this for each transaction. We actually do it for batches. Because like the bottleneck here would not be the CPU, like you can do quite a few like integer increments per second. The problem you would run into is that eventually you wouldn't be able to send as many network packets in and out through one NIC eventually. And so we don't want to run into this bottleneck. And so now that we have a write version assigned, there's another role called the resolver. And the resolver does pretty much what I showed in the optimistic concurrency control picture above. So it will keep all the writes of previous transactions in memory, and then it will get the read version and the write version, and it will just verify that the stuff we read was not written to in this conflict zone. We actually can shard this by key space, but like even one resolver can actually serve a pretty large cluster because all of this is in memory. And again, this only works because we have a 5-second limit. If you have long-running transactions, then you eventually run out of memory, obviously. But we only need to keep the last 5 seconds of changes and not even the values, just the keys that we touched in memory. And so this one will basically just return conflict or no conflict back to the proxy. And if it doesn't reply with OK, then we just throw back an error to the client and tell it that it didn't succeed. But let's assume it did succeed, because that's the more interesting part. Then we have another layer in FoundationDB, which is a distributed log. Think of this as a write-ahead log in a more traditional database, but it runs on like completely different machines. And we call into this distributed log and tell it to append it to a disk queue. And so this will actually make the transaction durable. So so this involves now a disk write and an fsync. This is the most expensive part of the commit pipeline. And so this one will do this again in order as the commits come in, and eventually it will acknowledge that it did that. And so now our transaction is durable. And so we can reply success to the client, and we have committed our transaction. Now, if you paid attention, you realize that in our commit pipeline, the storages are not involved at all. And so how do storages now get these updates? And basically, this happens asynchronously. So while this commit pipeline is running, storages constantly pull new updates from these tlog servers, and they actually receive the updates even before they are durable on disk. So if something fails, we might have to roll back some of these updates, but they only write it into memory. So it's very fast, because they don't have to immediately write them to disk, because if a storage server fails, it can just refetch the stuff that it lost again from this distributed tlog. And because of that, we have very rarely is like the case that a client asks for some data and the storage doesn't know about the version yet. It can happen if you have, typically if there are like networking problems, and then the client will retry at another replica, which will add to your like tail latencies. But in practice, we see this almost never. Like we actually log every time when this happens, and we might see this like once or twice a day on a large deployment. And once a second, each storage will tell the tlog system at which version it is, and so the tlog system can then eventually delete the data from its disk, because it knows that the storage has made the data durable. Okay, so this is basically how FoundationDB works, and like how you run transactions on top of FoundationDB. I now want to quickly talk about testing, because this is like one of the big like challenges in any system, right? And so if you think of like algorithms and data structures, testing those is typically not very hard. Like all of you probably implemented quite a few like unit tests for these kind of things. And the reason it's not very hard is because you can define functions over these data structures or algorithms and then verify that the functions do the right thing. And so just to remind you, like the mathematical definition of a function is that if you have two sets, then a function maps each element from one set to an element of the other set. And it does that deterministically. So if you give it the same value multiple times, you will always get the same result. However, doing this on distributed, like testing a distributed system is a whole other beast. Like it's very hard. And if you ever debugged failures in a distributed system, then you know that it's slightly more comfortable than pushing a fork into your eye. But not by a lot, right? It's like it's really, really painful and it's really hard. And so why is that, right? We need to, in order to solve this problem, we need to understand what the actual problem is. And the problem boils down to randomness here. So hardware, like all kinds of hardware, can fail and introduce randomness at any given point in time. Like you don't know how long a network packet takes to travel. You don't know how long a disk operation takes. And all of these things are very random. Now, randomness in itself is not necessarily bad, right? We have random data structures and we can test them pretty well. What makes this hard is that we don't have any control over the randomness. So if you have a distributed system and you roll this out to some cluster, you don't control the timings and the failures and these kind of things. Like the universe kind of decides how that goes. And then the other thing is that especially failures, but also like slowness, etc., is actually pretty rare, right? If you send 1 billion packets, then maybe 990 million of those will arrive in order and in a reasonable time, etc. But then you have like a few in betweens that get lost or connections that are dropped. So if you get into a failure scenario, then it will basically impossible to ever reproduce this anymore if it's a rare enough failure. And so you better got your logging and tracing and everything right, so that you can, without rerunning that test, actually figure out what went wrong. And so basically the claim I want to make here, that everything you can express as a pure function, you can test easily. Like, it's not very hard to do that. However, a distributed system in general is not a pure function, and it never is. It never behaves like one. And FoundationDB kind of solved this problem. And I like to, like, the profile pictures here are a bit weird, but if you don't know, this is the guy who replied here is the guy from Chepson. And Chepson is a person, like a test for distributed databases. And he developed this, and he would take commercial database systems and he would run some weird tests where he introduced hardware failures, etc., and see whether he can corrupt data somehow. And he got very famous because he could take basically any open source or commercial database system and prove that under certain failure scenarios, these databases will introduce corruptions. And so FoundationDB, like when it became generally available, like a lot of people started talking about this. And so this guy says, like, as long as this other guy hasn't tested this, I won't trust it, which is a reasonable stance to take, right? And this guy then just answers, like, I haven't tested this because what these guys are doing is way better than what I'm doing. And this is actually also the reason why Snowflake started to use FoundationDB, because our founders just got convinced that the testing is really so much better than what everyone else is doing. So what are we doing? We call this deterministic simulation. And so the high level idea here is that, first of all, each FoundationDB process is strictly single threaded. So we don't have any parallelism, but we have a high level of concurrency. We achieve this by having our own actor framework, which is like its own C++ extension that we call Flow. So if you're familiar with like C# or JavaScript, like you sometimes have these async await statements. And this is basically what we implemented in C++. And it uses stackless coroutines. The reason it doesn't use any parallelism is because parallelism introduces randomness that you cannot really control, right? Specifically, you don't control the operating system scheduler and the CPU and all these things. And then we in our simulator, and so now we have a simulator that can run these processes, and it implements all of our system calls in a deterministic way. So typically, if we run a FoundationDB cluster, for example, and we do a discrete, we would use an asynchronous function call, like system call. But in the simulator, it will use a synchronous one, because then you get kind of determinism. We also simulate disks, we simulate machines, network, and we also simulate time. That's a big one. So we control even the time in this simulated scenario. And now we can also simulate hardware failures, and we can inject them randomly at any point in time. And we do this actually way more often than you would expect in a real system to happen. And so a test basically takes now a test description, a random number as input, and some code version, right? Some PR. And so this simulated cluster, like this is now one process, right? One single threaded process. And it simulates disk, machines, network, as I said, and then it has a bunch of clients that it simulates, and those will run a workload on FoundationDB itself. And now we can make anything like fail in here. And then verify that the cluster handles this failure correctly. So, and because everything is in one process, we can even like define invariants over these distributed systems that have to hold at any point in time. So if someone introduces a corruption, we will catch that very quickly, like if some bug introduces a corruption. So a test description like this is roughly, like this is actually only a part of one of the simpler ones, right? It might do something like first it will define some workload. So this will be the first one, the cycle test, which is a transactional workload where each value is also a key. And if you take all key value pairs and you walk them, it will be a cycle of a given length. And then we run transactions that modify that cycle. And so at the end of the workload, we can walk this cycle again and verify that it wasn't broken or it didn't change its length, etc. And so if you have a bug in your transaction subsystem that introduces data corruption and you run this workload a billion times, then the chances are high that you hopefully break this invariance at least once, and then we will see this failure. Clogging will introduce random partitions, network partitions. Rollback will randomly fail storage processes. The reason it's called rollback is because in this case, we roll back the data in the storage and it has to like refetch that. And attrition will kill machines, simulated machines at random points in time. And in this case, it will only reboot them, so they come up with data. If you set reboot to false here, then it wouldn't reboot them. It would delete the data. And so that way we can verify that, like even on the certain data loss scenarios, we don't actually lose data because replication works as expected. And then all of the above will run in parallel. So this means the cycle test now has to function properly while you have a very unstable cluster underneath with a lot of failures. And so, as I said before, like now your test is basically a random number, and this random number is then used to initialize a deterministic random number generator. So we generate pseudo numbers to inject random failures. But that also means that if we run the same test twice with the same random seed, it will have the same outcome. So now it becomes deterministic. And if we forgot to add some logging to realize what's happening, we can add logging and rerun the same test to debug the failure that we're seeing. And then at the end of the execution, we return the last random number, which we call the unseed. This one we use to verify that actually the test was deterministic, right? So we run it sometimes twice and just verify that the unseed is the same. Non-determinism could be introduced, for example, due to memory errors. And then it also will reply with success or failures. And what does that mean, right? Now a simulation test is a pure function. So we have a unit test where the unit is actually just a full FTP cluster. And if you don't know, Snowflake is a cat company. So every Snowflake presentation needs to have a cat picture. And I think it's a happy cat. My wife thinks it's a scary cat. But I'm very happy about this because now we have something that is testable, something very complex. So how do we run those now? So we have, if you think about this now, I said like a test description plus a random number is an input for the unit test, which means that we have virtually an infinite number of unit tests, and we need to run many of those in order to get confidence that nothing breaks. And so Apple and Snowflake both test this like in a very expensive way. But to give you an idea of scale, we have a Joshua cluster, which is basically a work queue that uses a FoundationDB cluster. And so we upload a binary and all the test files that we have to this FoundationDB cluster. And then we have thousands of agents that download this binary, choose a random number, choose a random test to run that test, and write back the result to FDB. And that way we can run thousands of tests in a very short amount of time. Because remember, like we run the whole cluster in one process, which means that CPU-wise, like tests will be much slower than if they would run in parallel on like a real cluster. However, throughput-wise, we are still as good as a real cluster because we can parallelize this to like however much we want. And we have, I don't remember how many CPUs we have to do this, but it's I believe it's 3,000. And so during development, a user would send a test to Joshua and typically run 10,000 tests for a smoke test and 100,000 runs for more complex changes or for like finalizing the PR. But we say even for trivial PR, the minimum that a user has to run is 20,000. And that's actually what the CI does automatically for us. And then each night we run at least 100,000 tests on each branch. That's all changes. And when we finalize a release, we run typically in the order of millions of those and debug every single failure that we see. We sometimes, we saw like a year ago, roughly, like this number will be much larger because we scale our infrastructure more. But we made the math, and like the combined testing effort per year roughly corresponds to running FoundationDB on a chaos cluster for 4,000 years. And chaos cluster is a cluster with a lot of failures. And so this means that realistically, if you have an FDB release, you can expect this cluster to run for 4,000 years without any data loss. This obviously comes with some caveats, like we didn't forget to simulate some failure scenario in our simulator. Okay, so this was about testing, which is the one thing that makes me the most excited about FoundationDB. But I also want to just like very quickly give two examples of projects that we are currently working on, just to give you a sense what like the FDB team is, like the engineering work we are doing. One of them is we want to have more parallelism. So the problem is that each FDB process can only utilize one CPU core, as I said before. Which means that we can scale out pretty well. But if we have large machines, we cannot really utilize them effectively, right? Because we don't have any scale up. And this has problems like if you have 10 processes on a machine, then every client has to create 10 connections to this one machine because it needs to talk to each process individually. It cannot share any computational resources whatsoever. And so our solution here and what we are currently implementing is CSP, like communicating sequential processes. I learned about those in my programming class, I believe. But it's basically you have processes and they communicate through some queuing system, right? Go is a language that uses this extensively. But instead of doing this through threads, we do it through processes and shared memory. And the reason we do this, it's harder to implement. It's equally fast as doing it through threads, at least on Linux. Except for that you need to serialize because you cannot share memory. But it doesn't violate our testing. So we can simulation test this the same way as we would simulation test processes right now. The second project is Redwood. So as I mentioned before, we use the B tree from SQLite. The reason we do that is because SQLite is probably the most robust piece of software out there. And when FoundationDB was developed, they couldn't find a B tree that would survive their testing. Like all of the B trees that they tried would corrupt data after a while, except for the one in SQLite. We also have a few other storage engines. So there's an experimental RocksDB engine, which we don't plan to run because it corrupts data very quickly and very often. There's an in-memory engine, which is basically a standards map, C++ standards map and a disk queue. And there's also a Radix tree. This is the one that VMware uses. And now we also have Redwood, which started development at Apple and is now developed at Snowflake. And we have hired the Redwood people away. And this is a B+ tree, unlike SQLite, which is a B tree, with some interesting features, like it does some versioning and it's optimized for large writes. It does perfect prefix compression, which is something that is very valuable for FoundationDB and the kind of workloads that we are running. It's much faster than SQLite, so we are currently at the state where we cannot find a workload where SQLite performs better than Redwood, and it's very thoroughly tested through our simulation testing. But we also have like traditional unit testing, etc. Remember, this is a data structure, so you can actually unit test it. Quickly, why do we do that? So most people are like, why don't you use an LSM? LSM are like the nice thing today. So the main problem here, I don't want to go too much into the weeds. Like this is often like a very emotional discussion, but basically LSMs don't work very well for us, mostly because they require a tuning for the workload. Otherwise, they don't perform typically very well. And as we are kind of like a cloud provider, we don't have any control over the workload. Our workloads can change very quickly, and our workloads are different depending on which deployment you're looking at. There's also other problems like range deletes are very expensive, which is a problem for us. And like there are a few other details. And so we decided that a B+ tree would be the right data structure for us. Redwood can do batched updates, which most B+ trees are not very good at. FTB writes to disk every half a second, so we have a lot of batched writes. And then, as I said before, the key compression, it perfectly integrates in our testing. It's written in Flow, it uses our actor model. And then there's also just like the benefit of having an in-house storage team. So currently we are working on encryption at rest in the storage engine. So instead of just encrypting the disk, we want to do this in the storage engine itself. And this is just much easier to do if you have engineers who understand like the internals of the code very well, if it's an in-house product. Like this is probably the weakest argument because you can build this knowledge for any system, but it's still an additional benefit. Okay, so I'm done, and thank you, and I can take any questions that you might have.
Perfect, thanks a lot.
Thank you.
And do we have questions from the audience? Yeah, go ahead, Matti.
Yeah, so thanks. I love the total testing stuff, but I'm curious as to, you know, is that, I mean, it's pretty thorough, but is that your, you know, entire strategy for ensuring correctness? I mean, how are these things engineered? Have you looked at, you know, things like applying something like, say, formal methods to ensuring correctness, or are there areas where you try to, or how do you try to construct this thing so that you can sort of reason about its correctness, as well as run it for, you know, effectively 4,000 years in a chaotic environment?
Yeah, I mean, so it's not our entire story for correctness testing. There are some things that are not run in the simulator. For example, all the system calls and the way we call them. So our file system layer, for example, is simulated in the simulator. So we also need to test it outside of that. And we also do chaos testing on real clusters, mostly because there's certain like availability guarantees that we want to have, and these are usually very, very hard to prove in simulation. So we more like test it, like we inject failures and then we measure the time it takes the cluster to come back to life, etc. So and then there are a few other things we do. The client is multi-threaded, so it cannot be entirely simulation tested. Most of the client's code is simulation tested, but not all of it. And so and that is actually where you also will find most of the bugs. Like most of the bugs we see in production are actually in the client. And for the client, we need a better testing story because we run into problems there. We did not look at formal methods. I proposed this before, but we didn't have the time and the expertise, honestly, to do this thoroughly. And having something like this testing infrastructure also comes with problems when you come up with like clever algorithms. There are a few things in FDB like that are very clever. Like some people who are way more clever than I have worked on those, and they sometimes rely on properties across the whole system that when you look at them and explain it to someone, then everyone's reaction is like, you have to be insane to implement this because this is too fragile. But we rely on the fact that our testing is very good in finding bugs in the implementation. And so it definitely has its problems, and it's not perfect. And I would say the biggest problem is everything that works together with gray failures, right? Where you are like, okay, in theory, FDB is allowed to go down in cases of gray failures, like it can just stop doing anything to protect its data. But you don't want it to if it's not necessary, right? If you still have enough resources. But sometimes it still happens. Like we have outages because FDB just becomes unavailable for some very weird network failures. Like one example that I can give you is an availability zone failure where existing connections would still work fine, but you cannot open new connections. We had this once. And then FDB would believe, like the master process that runs the recovery algorithm just believed that everybody else is down, but it wouldn't get replaced because the coordinators that elect this guy could still talk to this guy. So they were like, oh, we still have a master process. And the master process was like, I don't have enough other disks to recover myself, so I'm just not doing anything and wait for the administrator. And that was a pretty bad one because we also couldn't SSH into the machine and kill it. And so it took us roughly 10 minutes to resolve the problem. So these are our main challenges when it comes to testing.
Cool, thanks.
I have sort of a
Daniel, I think we can't hear you. Are you speaking?
I could hear him.
Oh, you could. Okay, then maybe it's just me. Okay.
No, I couldn't hear him. Can you try again?
Can you hear me now?
Oh yes, now it's good. Yeah.
Okay, cool. Yeah, maybe my headset does weird things. It's Bluetooth, so you never know. Yes, hi. I'm Daniel. I had sort of a follow-up question to Mossi's question. Right? So. Yeah, so you run this thing sort of a factor 4,000 basically, right? Like in a chaos cluster. So that the probability that anything that you test turns up in your tests instead of in production is pretty good, right? But I guess like it's still testing. So anything that you don't think of while writing the tests that doesn't depend on the randomness that you inject is still not tested. So my first question is sort of how often does that happen? And what is your sort of story? Can you then, like, how do you then write, like if you encounter something in production, how do you then reproduce, or how do you then write tests that in the future would cover something like that?
That's a very good question. So this is indeed a problem. Like we don't, like the benefit of simulation testing is you don't need to write tests where you have to think of all possible corner cases, right? Because the simulator will take care of a lot of that. But if you write a new feature, then obviously you need to have a test that actually exercises that feature. And we mostly enforce this through proper code review, and every feature has to go through like an engineering review where you have to convince like architects and which would typically be me, that you did your proper testing, which also includes performance testing, right? And that is working really well in my experience. Like we never had a feature that we accidentally didn't test. However, where this kind of gets more interesting is combination of features. Right, and this is actually the only bad bug that we ever had on a QA cluster. It didn't make it into production, luckily. Where basically we have a locking feature where you can lock the database so no read or writes go through. And then we also have, I try to remember what it was, the other thing. I believe it was the snapshotting feature where you like snapshot the whole database in a consistent way. And if you ran these two things together, it could introduce a data corruption. And the reason the simulator didn't catch that was because we simply didn't have a test that did the two things together. And I had to make a whole apology tour through the whole company for not catching this before it went to a QA cluster, and it was really bad. Another thing is like upgrades are very challenging to test properly, right? Because now you have potentially processes running at different versions in the same clusters, and that is not something that the simulator does. So we just make sure that two versions of FDB can never ever talk to each other, which is an operational challenge, because now if you want to upgrade, you have to do this atomically across the whole cluster. So yeah, I mean, that's to answer the question how often it happens. In the last like 5 years since I'm working on FoundationDB, I have seen it once, making it out of simulation testing, which is a pretty good track record, but obviously making it out into production once in 10 years is kind of what we expect would happen. So we expect to have one disaster every 10 years, or at least that's kind of what our founders are telling us, that that is their expectation. And so far this didn't happen, but it probably will eventually because of what you just said.
Okay, and then, so I mean, and then once then you're back to the fork in the eye debugging, right? I guess, or does simulation testing then somehow also help you with reproducing bugs that are then basically non-deterministic, like fully non-deterministic?
We need I mean, usually we are back to debugging the traces. So we write every FTP process, including the client, writes log files to disk, and these log files are automatically ingested into a Snowflake database and replicated to a different region. So even because if we corrupt FoundationDB, we cannot read our Snowflake database anymore. So we need to have a replica somewhere else in case that would happen. And so if we have a production incident, typically it's an availability issue, luckily, and not a corruption issue. We use these files to figure out what happened. And in most cases, we get a pretty good idea, but there have been cases where we just didn't really know what went wrong. And in that case, where the simulator helps is you can write tests that simulate what you believe went wrong, and then you can observe whether the behavior is the same thing as what you observed in production. And that has been successful in the past, but it's not perfect. So yes, you could run into a production incident where you see you clearly had a bug in FoundationDB, but you have no idea what went wrong.
Okay, yeah, thanks. And thanks for the talk.
So I had a question more towards the beginning of the talk. You mentioned having like a logical warehouse per application and per user. I'm sort of wondering that design decision, is it motivated mostly for security reasons, like isolating metadata and data from users, or I mean, I guess there's also implications in just how you are able to disaggregate things and design the system architecture. But I'm sort of wondering what are the main things that drove that design decision and the implications?
I think you're talking about.
You mentioned like Apple. There was a slide where you said Apple. Yeah.
This one, right?
Yeah, exactly.
I always have to be very careful when I'm talking about Apple because we have an NDA with them.
Okay.
But so there's a paper, and I can cite everything that is in that paper, obviously. And I believe, so the reason for this is they want to have these very small databases because that allows them to move data across different clusters very quickly. So if they have a user that is very active, they can quickly move it to a different cluster. And I think that was the main motivation. Yeah, and they don't need transactional guarantees across multiple user and applications. Okay. And so that's how they are getting away with that.
Okay, that makes sense. Thank you. Any other questions? I will stop the recording.